Precalc, this is 2.9. We're going to talk about one-to-one functions and their inverses. Basically, if something is one-to-one, it will have an inverse that is a function. So, to be one-to-one, you also have to test if it's a function, because it's a one-to-one function. So first, it has to pass the vertical line test. Then, we can go back and test a different test to tell if it's a one-to-one. But let's go recap. All right, now I have two sets of mappings. You guys remember what mappings are? Where you take your inputs, map them to the outputs, and it kind of shows just a direct link between inputs to the outputs. Like in the first set, 2 will always go to a 3. A 6 will always go to a -7, -4 goes to 0, and 0 goes to 7. That, ladies and gentlemen, is what we call one-to-one. What does it mean? That it says that every input has its own output. Or, above, it's a function in which no two elements of A have the same image, and I forgot to put in there, in B. Okay? So, everything that goes in goes to its own output. The second group, the -4 and the 0, both go to 0. If you guys are wondering, yes, that's still a function, right? Because no input is going to two different outputs. So that's still a function, but it's not one-to-one. Everybody on the inputs does not get to go to their own output. So that's why the second group is not. We also can look at it in terms of f of x1 and f of x2. Essentially, no function or the value of f of x1 should ever equal f of x2. That's what it means here. Or, if they happen to be the same value, the only reason that can be is if the values going in are the same. And we're going to use that fact to prove things are either one-to-one or not one-to-one algebraically. The only way for the outputs to be the same is if the inputs were the same. To be one-to-one. Okay, page. So, we have the vertical line test that tests for functions, and we also have one now called the horizontal line test that would test if a function is one-to-one using the same type of logic. If a horizontal line, any horizontal line, can only touch the graph, if it touches more than once, then it is not one-to-one. Or if it does, then it's not one-to-one. And I put on the bottom or underneath that, it says that if you tried to prove something is not true, or proving something that is not true, is easier than to prove that it is always true. And I like to use that analogy of if you want to be really super creepy and follow me around in my car, every time I get in my car, just to prove that my statement of I always use my directional every time I turn is true or not true. You can follow me around for the rest of my life every time I get in my car to watch, make sure I don't do that. But as soon as it takes me one time of me turning without it and you saw it, done, right? Or if I said, hey guys, I was in Wisconsin Dells this weekend, which I was, but then all of a sudden on Saturday afternoon you saw me at the mall or something, you'd be like, no, there you are right there. You can't be in the two places at once. Just a counterexample, right? You prove one, you have one counterexample, proves the whole statement wrong. You don't have to go any further. You don't need to find me somewhere else in Green Bay or not in Wisconsin Dells. Or follow me around again to find out that I don't use my directional aid again. Once is enough. So, in part A and B here on this one is you need to decide, is it a one-to-one function, yes or no? So I'm going to do this both ways. I'm going to show it graphically, and then if we don't have a graph, like we don't now, maybe we should show it algebraically that it is or is not. Now, that first one is an x cubed graph, if I remember correctly. So, we remember what an x cubed graph looks like. Kind of. It would start below and turn up like this, yes? So we would have a graph that looks like this. probably the first thing we should do is test, does it pass the vertical line test? Does it pass? Yes. So it's a function. That's good. We now can go and test if it passes the horizontal line test. And the horizontal line test results say, yes, 1-to-1 function, right? So we have a 1-to-1 function. That's perfectly fine. That's great. But we didn't have a graph in the beginning. So is there some way we could do this without? So mentally, we know that it will turn into a 1-to-1 function. So can we go back to this statement here? Can I prove this? Or can I show this? So, if we said that statement, let's just assume that I put in two different values into our function. Can we say that, hey, I am going to put in f of x1 should equal f of x2. If I put two separate values in for x, I don't know what these are yet. They would have to end up being the same for it to be 1-to-1, or they end up being the same, right? If I wanted to use this, at the end we need to show that x1 is equal to x2. And if that's true, then we're good. If it doesn't come out that way, then we know we don't have a 1-to-1. Well, that's just function notation to put it to here. So the function is x cubed. So x1 cubed equals x2 cubed. And if I wanted to get them by themselves, what do you have to do? Both sides. I want to get rid of the cube. Cube root. If I take the cube root of anything, I get an answer always, right? Just one answer. The answer happens to be x1 is equal to x2. Check, therefore, 1-to-1, yeah? It's a 1-to-1 function. x1 is equal to x2, which what we said has to be true. If I moved on to the second one, it's a parabola. Is it a function, first of all? Yes, it passes the vertical line test. Is it? Pass the horizontal line test? No. So this is not 1-to-1. But if I wanted to show that algebraically, some of us might be like, oh, okay, well then can't I still do this? And it shouldn't work, right? That means that x1 and x2 might not be the same number. Because, wait a minute, that means this would have to equal this, right? But here's the thing. When you square values, what happens? Yeah, there could be potentially the same answer from two different numbers. So in this case, yeah, you're like, oh, just square root, and then you'll have an answer, right? But don't forget that when you're square rooting, that really there's a plus or minus that goes into effect, right? So we have to kind of worry about things. So therefore, I can't really use this method. But since I know from the picture that it does not work, can I give a counterexample? Give me a counterexample. If x1 equals what? What's that? 3? Then x2 will have to equal -3. And what happens? F of 3 equals f of -3. Trying to put a negative in there. -3. Which is 3 squared equals -3 squared, which is 9 equals 9. They're not the same value going in, but they give us the same value on the way out. We just gave a counterexample of 3 and negative 3. That is true, but not the same input. Therefore, not 1 to 1. Just gave one counterexample, done. Not 1 to 1. So if I ask you for this one, is it 1 to 1? And so f of x1 should equal f of x2, right? This one's saying show that it is. So basically on this particular problem, the way it's worded, it is a 1 to 1. So we can definitely use this. And so it's 3 times x1 plus 4 is equal to 3 times x2 plus 4. Subtract 4 from both sides. 3x1 equals 3x2. Divide both sides by 3. So x1 is equal to x2. Check. 1 to 1. The next part, guys, is talking about inverses. This stuff is pretty simple. The fact that what we're talking about is if you let f be 1 to 1 function with a domain A and a range B, then its inverse function, inverse f, with a little negative 1, has the domain now of B in a range of A. So the domain and range will also switch. The inverse function of y is equal to x if and only if f of x is equal to y. Basically what it means is that your x and y's will switch. The inverse, if you think about it this way, guys, inverses put you back where you started, right? So if this function, if I start with x and I get y, its inverse function starts with y and gives you x. So now it just wants you to find the inverse of these 3 here. If f of 1 is 5, f of 3 is 7, and f of 8 is negative 10, then what is f inverse of 7? The answer is 3. F inverse of 5 is 1. F inverse of negative 10 is 8. Now take a look at this once. I think everybody, if you looked at this function notation, can you give me the 3 points that are connected here? What's the first point? Function notation. What's x? What's y? So you get 1 comma 5. This is f of x, right? What's the next one? 3 comma 7 and 8 comma negative 10. Inverse, f inverse of x, the first point is, or actually it's this one, the second one on here, but if I put in 5, I get 1. If I put in 7, I get 3. If I get negative 10, I get 8. What did I do going from the function to its inverse? I take all the x's and the y's and I switch them. So all of the inputs become the outputs become the inputs. The range becomes the domain becomes the range. Everything about them switches. Start with 1, you go to 5. If you go to 5, it puts you back to 1. Their inverses put you back where you started. The next slide is going to use that very much to your advantage. Questions? Can I change the page? This is something we've done in Algebra 2, Geotrig, and I'll read it and then I'll make it larger so you guys can get it easier off the board. It says if you let f be a one-to-one function with domains A and range B, then the inverse function f inverse f of 1, f inverse, satisfies the following cancellation properties. And it states that you can put one inside of the other. And I'll try to make this larger here. It says that if you take the inverse of f and you put f inside of it, it brings you back to x. If you take f, the function of its inverse, it also brings you back to x. In the years past, you would have used f of x and g of x. G of f of x and f of g of x. You guys remember that? And they always should lead you back to getting x, because that's what you start with. Conversely, any function f inverse satisfying these equations is the inverse of f. So if this is true, and remember, not just once, but both have to be true. So you have to put one inside the other and the other back inside the first one. And if they both give you x back, then we are inverses. Notice the wording, verify, which means they are inverses. You got to show me why it works. Notice they use f of x and g of x for this particular problem. So you need to show this is true and that is true. And if both of them are true, then they're inverses of each other. So guess what? Because this happens, later on, the next slide is going to ask you to find inverses. And when you find an inverse, you can check it using this process, and you will know if you did it right. F is the outside function of x cubed. So I took the x out, and I'm putting what inside? G of x, which is x to the 1/3. What is x to the 1/3 to the third power? X to the first, which is x, because power of a power you multiply. So it worked that way, and now I got to move on to the next way. G of x, which is the outside function, is to the 1/3 power, where f of x is x to the third power, which just leads us to x to the first power, which is x. So therefore, inverses. You've done that already, at least 2 different years. This will be our 3rd time approaching this topic. Now, the example they gave is fairly simplistic. Don't be afraid that sometimes there's going to be multiple x's where you have to sub in, that you may have to distribute, you may have to FOIL, you may have to do a couple other things, right? But this is the process that needs to be done. So, it's all great to have one-to-one functions, to prove that something's one-to-one. We proved that things are inverses, so we talked about using inverses. Now, let's find inverses. So I give you a 3-step process, which is slightly larger than I usually do, because in this book, we like to also state things in proper function form. So that's why we'll always start off with, a lot of times, of f of x equals instead of y equals. So in step 1, I would like you to write y equals instead of f of x equals. Change it to a y. I think if you change it to a y, it's a little bit easier to work with. Step number 2, switch x and y. Step 3, solve for y. That's it. I also put on there, as a big reminder, remember that the original domain and range will also switch. So you end up switching your domain and range for the inverse. Because all you're really doing is switching your x's and y's. I also wanted to add a note in there that the inverse of f is obtained by reflecting the graph of f about the line y equals x. And if you want to know the line y equals x is the one that's like 1, 1, 2, 2, 3, 3, and so on. So basically it mirrors it across the other side. If you graph both of them, you'd be looking like it's a mirror right here. Okay? So, I've got a line, I've got a fifth root, something to the fifth power, sorry, and then I have a square root graph as the third example. So, the first two, we don't have to worry about too much because y equals 3x minus 2, which should be my first step, is a line. And what do we know about the domain and range of all lines? All real numbers, except for a few exceptions, right, of the horizontal and vertical. But this is all real numbers. So if I switch it to its inverse, the domain and range are still both all real numbers. Not that big of a deal. So let's do this. Let's find its inverse. First step we already did. Second step says switch x and y. Whoops. And now solve it for y. Add 2. X plus 2 equals 3y, and divide both sides by 3. If you were to look in the book, this is what they give you. They said, yeah, this is fine. Now, there's one last thing that I would possibly want to do for this, or two things. I don't want to say it's y equals, because the y equals was our original function. This is the inverse. And so, I will put a little -1 above that y to say this is y inverse. Or change it back to f inverse of x, right? So, you can use function notation for that, or say y inverse. Now, if I had to use this graph, guys, I probably would not keep it in that form. I personally would have changed it to say what? Common denominator, x over 3 plus 2/3, right? That's a little bit easier form for me to look at or use in the future. Again, the book would probably use the all over 3 because they just said find the inverse, but I would separate it out. Any questions? Okay, the next one. Do the same thing. I'm going to give you guys some time for that one. It is x to the 5th minus 3 over 2. So y equals. Okay, should have been enough time. Switch x and y. Oops. Switch x and y. So x equals y to the 5th power minus 3 over 2. Then multiply both sides by 2. 2x equals y to the 5th minus 3. Hey, what's so special about this one again? Going to add 3. What's so special about plus 3. What's so special about this y to the 5th, or a 5th power function? What's so special about their range and domain? Guys. It's all real numbers again. So you could change that to f inverse of x, but it's the 5th root of 2x plus 3. I'm hoping you guys will remember, I think that's something like the 5th root right there. It would look something like that, right? Got 4 different changes going on. So it's all real numbers, and it's going to go up and down forever, all real numbers. So our domain and range of our inverse will also be all real numbers. Not that big of a deal. To not really talk about it too much about that. Is everybody okay with that? But when we get to our last problem, there is no b. Okay, get that out of there. If you get to this last one, it's a square root of x minus 2. If I wanted to talk about this one, what is the domain of this problem? What is the domain of the square root of x minus 2? Where does it start? It starts at 2 and goes up. X is greater than or equal to 2. The range, on the other hand, though, starts where? Knowing square root graphs. Guys, this graph if I'm thinking about the parent, family, child, which way is it going? Which way is it moved? 2 to the right. Is it going up or down? No. Well, it's not translated up or down. It's opening up. You're correct. So then y is greater than or equal to 0 still, right? Or you guys would say, here we are, there's the graph. Just a quick graph, right? Not drawn to scale, nothing perfect about it. But here's the thing. When I find my inverse, now the domain and range will flip. And so, let's find that. Y equals the square root of x minus 2. X equals the square root of y minus 2. Square root, or square both sides, so x squared equals y minus 2. Or y inverse equals x squared plus 2. Switching the sides around. You're like, oh, that's just a quadratic. That's a parabola that opens up, right? A quadratic that opens up and was translated which way? Up 2. Guys, we're using this, this ability to know where graphs are being moved from their parents. This is good. And then you would say, oh, but here's the problem. We know that a quadratic is all real for your domain, yes? But not this time. This time, x only exists, x is greater than or equal to 0. Why? Because it's this one. Our range is now this one, where it's y is greater than or equal to 2. But wait a minute. So that means I'm only taking the positive side of a quadratic. Let's go back to our graph. Wouldn't that start here and go like this? Hey guys, guess what? Didn't we say that it was supposed to be reflected about that line? Doesn't it look like a mirror image now?
Maybe.
Possibly. I'm not the best drawer, right? So that's what we're taking from this problem. That's why I added this one, is because the inverse function has a different domain and range than what a normal x squared graph would be. Very interesting, isn't it? Take that in consideration when you guys are graphing things or talking about where things are true or not true. Can I turn the page? Because there it is. Homework is on page 236, 1 through 69, every 4. Have a fantastic day.